what we're going to do is interpretation of Excel and STATA output. Okay. So I have some data here, X and Y. There are 10 observations, and I want to regress Y on X. Okay. So I just copy this table, and we'll do it both in STATA and Excel, this regression, and interpret the coefficients. So this is STATA. Let's go to Data, Editor, and paste, and exit. Now you have the variables here, X and Y, and you simply do this: regress Y on X. You can click them or type them, and bam, it spits out a table for you. The exact same table is the one here, or it should be the same at least. And then we can do the same thing in Excel. Excel is here. Copy paste like this. Okay. Then let's zoom out a little bit. Data, go to data analysis, regression, press OK. Output range. Select the output range, press enter. Then select X range, enter. If you have two X variables, you select them both at the same time, okay? Labels, that means that the top one is labels. Confidence level, okay, the 95% is fine, okay? I don't want to change that. We want a constant, so it's not 0, okay? Then you just press OK. And bam, it just spit out a table for you as well. So that's how you do this part. Now, let's interpret the coefficients. We'll first start with the best fitting line. Remember this equation? This is equation of the best fitting line through the points. The points don't all lie exactly on the line. So what results do we need to look at to know the equation of the best fitting line? Well, I need to know the y-intercept and the slope, and then I know the best fitting line. Okay. So let's try and graph it a little bit here. Okay. Okay, it's just like this. Let's try and graph it like this. So anyway, the whole point is you have some points. Okay, like this, like this. Now they're not that parallel to each other. Okay, but the whole point is there's some best fitting line and it's positively sloped because I can kind of tell from the data, right? If you see the data, both of the time series, both of the variables are kind of moving together. As one increases, the other one increases. So I have this. This is a scatter plot. So my x is here and my y is here. Okay. And this is the y-intercept here. So the point on the y-axis, where the line fits, this is the alpha hat. And the slope means if my x increases by 1 unit, okay, by how much is my y increasing by? Well, it's the beta hat. That's the increase in the y, on average, of course, because the results are on average. So let's remind us, so the best fitting line through the points is like this, yi equals alpha hat plus beta hat times xi. Okay, and that is the best fitting line there. And actually, the program estimated some stuff for us, that the y-intercept is 60. And it makes sense because there's very big y values and very small x values. So a 1 unit and the intercept is 60, and a 1 unit increase in x, it says the slope is also 5. That means it will increase y by 5 on average. So what do we see from some of the first results here? And you can see there is a STATA results, and they are the Excel results. And if we just double check real quick, okay, I think it looks about the same. So this seems, yeah, I think it's about the same. And if you actually compare the two STATA, the STATA and Excel, you see a lot of similarities, okay? In general, they should be actually pretty much exactly the same, the results, okay? So let's see. What is the alpha hat? Oh, it's 60. And the slope is 5. Okay, so we go here. Okay, so the y-intercept is 60. And what is the interpretation of this y-intercept? So it's 60 here on the y-axis. It's when x is 0. What is y? And in particular, y on average. Because remember, when we talk about the regression, the results are on average, right? So y is 60 on average, okay? And then the beta hat, when x increases by 1 unit, by how much does y increase? I didn't draw it to scale here, but this should be 5, okay? So anyways, you can just write the best fitting line as follows. 5 plus, oh, not 5, 60, okay? Plus 5 times x, xi, okay? It's the best equation of the best fitting line here, okay? And it's actually kind of the main result behind the regression, right? Is this best fitting line, because it models the relationship between the two variables, and it's a positive one, okay? Let's continue on now. The standard error S beta hat. This is the sample standard deviation of beta hat, and is related to the sum of squared residuals, and is related to the sample size. So the better the points fit the line, this will be small, and the bigger the sample size, this will also be small, okay? And yes, so this is analogous. Remember our x bar and our univariate statistics? This is analogous to your sample standard deviation of x bar, really, okay? But now we're looking at these coefficients, not x bar, but beta hat instead. Okay, so we see as 0.58, okay? And a sample standard deviation again of this beta hat, okay? Where do we find it? It's right over here, okay? And it's computed. You can compute it by yourself if you know what is this MSE. Well, it's coming soon. Okay, so we'll talk about that. And now that we know the beta hat and the standard deviation, we can conduct a hypothesis test. Because if you recall, okay, slides here. If you recall that that in order to conduct a hypothesis test, what are the new and alternative hypotheses? Is that the true beta in the population is 0, and the alternative is that it's not 0. And what does the 0 represent? Means there's no relationship between X and Y, if you remember. That means there is a flat line in the population. Flat means this as X increases, Y doesn't tend to increase or decrease. It tends to stay on the same level. That means there's no relationship between X and Y. Okay, like this. And if it's not equal to 0, there is a relationship. Yes, relationship. Okay. Okay. If you remember, in order to conduct the hypothesis test, what did we assume? We assumed this. You have to go back to this estimator theory and this distribution of this beta hat, right? And it turns out to be normal, right? And then it turns out to be normal with what? Well, it's mean. It's centered at the true beta, always, right? And if you remember, as some kind of variance, okay, is the variance of the model, if you remember, times the sum of these xi's, okay, and x bar squared. So this was the variance, if you remember, okay. But anyway, long story short, if I take a sample, I estimate this by what? By the mean square error, okay. This is how I estimate this sigma squared, okay. And now this is kind of the sample variance in the sample, because I can compute that, because I don't know the sigma squared. This is the population variance of the regression model, okay? And then once I know the distribution of beta, I can conduct the hypothesis test. And how does it work? Do you remember? I assume the new hypothesis is true. So the process is exactly the same as the univariate case. If you remember, with x bar, we assume that mu naught is true. Or mu naught in this case, remember, it was like equal to 3.5. But now, we assume it's true, so we assume that beta is equal to 0, and we try to find evidence to see if we can reject it, right? So that's how it works. So you can compute the z-value, if you like, which is also equal to the t-value in terms of computation, if you remember, okay? And basically, it's what you'll do. It's equal to beta hat minus 0 divided by the standard deviation of beta hat. And what is standard deviation? Is the square root of this mean square error divided by the sum of the xi minus x bar squared, okay, like this. And bam, you can get your test statistic here, okay? And see if that is beyond the cutoff points or not. And if it's beyond the cutoff points, you're going to reject the null. And it's easy as that, okay? Okay, so that's how it'll work. And of course, what is this thing, this MSC divided by this sum here? I just told you this is the standard deviation, or let's call it the sample standard deviation of this beta hat, right? Beta hat is the thing that's here at the bottom, at the denominator, okay? S beta hat that we just computed. So you can conduct the hypothesis test like this, and let's see some numbers, okay? Okay, the t value or the z value, they're the same, but the programs, they always use the t cutoff points because they want to try and be conservative. Remember, the t is, especially for low samples, it's a little bit more spread out than the z. So the t cutoff points in this case will be a bit more spread out, if you remember. And how many degrees of freedom is t going to have? Oh, it's going to be n minus k degrees of freedom. So this will be the cutoff points with n minus k degrees of freedom. In this case, n, my sample size is 10. K is the number of parameters to be estimated. How many parameters are there? They are the y-intercept, alpha hat, and beta hat. So there's two parameters in this case. So my degrees of freedom are 8. Then I look at the table to see where the cutoff points are. It's going to be plus minus some cutoff points, some t values. So it's going to be t for 95%. I want 0.025 to be on the right side of that one. Comma 8 means this is degrees of freedom, right? I want 8 degrees of freedom. If I look at the table, it's 2.306. So it's plus minus 2.306, and those are the cutoff points, okay? And then I can do the hypothesis test. And anyways, is there the t-value here? Oh, look, there is a t-value. And how is this t-value computed? Well, I need to go back and look at the picture. It's basically just the beta hat. Let me just write it here. Right? This is equal to the beta hat divided by the S beta hat. This is the t. Okay? This is the t. So, in theory, the 5, now again, this is the coefficient on x. That means this is the beta hat. Again, it's 5. Okay? Let's not confuse ourselves. It's not the 60. So the beta hat is the 5. Then you just divide the 5 by the standard error, which is 0.58. And it should give you the t value. So you can double check with the calculator, divide this by this, and then you should get the t. Okay? So this is not that hard to do, right? You can do it on your own, but even the program spits out the t for you. By the way, on the exam, notice that there is a lot of redundant information that the table is spitting out for you. For example, the t value, well, this can be computed. Just divide the coefficient by the standard error, it'll give you the t. So now it's redundant information. I don't need this information, right? On the exam, I'm going to leave some stuff blank in the tables. And based on information that's already given to you in the tables, you should be able to compute them out. For example, like the t. If the t is blank, you should be able to compute it, right? Okay. Then, the program also gives you the p-value. Remember what the p-value is? Well, it turns out the t is pretty big, so I'm going to be rejecting the null. It's beyond the cutoff points. In particular, it looks something like this. If you're going to draw it, let me delete this real quick. But if you're going to draw it, what are you actually doing is you have this distribution here of your beta hat, and you assume what? Remember this? It's a normal, right? And it's centered at the beta. And you estimated the variance, which is MSE over the sum of the xi minus x bar. Okay. So you kind of estimated this, if you remember. And you assume it's centered at the new hypothesized value. So it's centered at the zero mark in this case. Okay. So this is the beta hat, but it's centered at where my beta equals 0. Because I assume the new hypothesis is true. That means that I got a beta hat that's very far down. Okay, my beta hat is equal to 5. Right? It's equal to 5, but 5 was all the way here. Okay. So what is the p-value? The probability of me getting this beta, this extreme or more extreme. So that is the p-value here, okay? It's this, and beta is minus 5 here. I have to put it here as well because it's like a two-tailed. It's a two-tailed one, right? It's equality is there, if you remember, okay? So it's the probability that I'm getting a beta that's this extreme or more extreme. So it's this plus this. And basically what I just did is I transformed the whole thing into the z, and then I just get bigger than the z values. instead of the beta hats, right? Because I transform into the z, okay? Actually, the t, right? I transform into a t according to the program, right? That was the t, not the z. So we have to be a little bit more careful, okay? But anyways, let's see what the p-value the program computed for us. Do you see this 2.55 e to the negative 0.5? What does this mean exactly? Well, this means 2.55 times 10 to the negative 5th power. 2.55 times 10 to the negative 5th. How do you read this? Okay, this is the Excel output, which is similar actually. Oh, that's why we're in Excel here, not the STATA, okay? So 2.55, so to help you understand this, it's like this. So these areas are very, very small, okay? And the Excel output is written like this. E minus 0.5, I think, or something like this. But what is this equal to? 2.55 times 10 to the negative 5th power. Times 10 to the negative 5th. And if you did this in high school or whenever you did it, like I remember it to this day at least, you have to move the decimal point 5 spots to the left. Okay? So it's like this. 1, 2, 3, 4, 5. And you put the decimal point here now. From what I know. So it's 0, 0, 0, 0. 4 zeros and then the 2. That's how you read this, okay? This is what it's equal to. Okay? So this is very, very small. So these areas that I'm drawing are very, very small. So this plus this one, this is equal to negative 5, okay? They're very, very small. Okay? And again, what the program does is convert this to the t distribution, and then it computes those for you. So you don't need to worry too much. Okay? But on the exam, I don't think you have a table that's this precise, so I'm not going to ask you to compute the p-value. But in theory, if you have a precise table, you should be able to compute it on your own without asking the program to do it for you, right? As well. That you have just enough information. If you have the t-table, there should be no issues. But a precise t-table, unfortunately, this is not the case. Okay? You have to convert it into the t distribution, okay? Okay. So let's continue on. Okay, so the t-value is like this, right? Yes. And we calculate it, and then the p-value. Oh, okay, with 4, right? 1, 2, 3, 4, and then yes. So it's very, very small. 10 times to the negative 5. Okay. Since the p-value is less than 0.05, which is the significance level, and this is like our standard, right? For the 0.405 significance level, I'm going to reject the null hypothesis that b is equal to 0. I accept the alternative. And what does this mean? That means, yes, I conclude that there is a relationship between the variables, a significant relationship between the variables, you can say. And if you want to be very technical, you can say statistically significant relationship between the variables. Statistically significant, not just significant, okay? You should add this word statistically significant. And lastly, what the table reports, so it reports the p-value, and then reports this confidence interval, which, okay, remember the 3 tests I can do, they're all equivalent. The t-value way compared to the cutoff points, or the z-value compared to the cutoff points, whatever you would like. The program does the t. Yeah. The p-value, right? This probability make sure it's lower than the significance level, than the alpha, which is not this alpha, but the other alpha, the significance level 1. Okay, it's not this one. So don't confuse them. It's not the 1-intercept here. And then You got the confidence interval. And how is this computed? Just by our standard formulas from before. This exact same way as before. So what you get is your point estimate, which is 5. So everything will be plus minus this 5, okay? 5 will be centered at 5, and you can double check if this is the case. And another way to test the an alternative to do the statistical test, see if the null hypothesized value is inside the confidence interval. In this case, is 0 in between these values. And the answer is no, it's not in between. Therefore, I reject the null hypothesis, okay? But anyway, what is the form of the confidence interval? It's like this. The probability that the true beta, the population one, is between these two values is 1 minus alpha, in this case 0.95, right? I'm 95% confident. It'll be centered at your point estimate. This is your best guess for the population beta. These are the cutoff points. Remember, the same thing as before. And this is the sample standard deviation of your beta hat. Same thing as before. Before this was, remember, it was your S divided by square root of n. Remember? And now it's this square root of MSE, which represents the S now, divided by the sum of xi minus x bar, which is the standard deviation of beta hat. And before it was the standard deviation of your x bar before. So the analogy is exactly the same as before. And then you just replace by the values that you see on the table. Okay, and you already know the cutoff points are 2.3. We computed them earlier. 5, the beta hat, and 0.58, the standard deviation of the beta hat. Okay, the same thing as before. N minus k are the degrees of freedom of the model. So these are the main degrees of freedom. And where do you find them? Right here. Degrees of freedom of the residual. This is the main one. It's 8. 8. Okay. 8. So this is the main results of the regression. But the table shows a few more things that you should also know. There is something called multiple R. This is 0.95, if you see. And it's right over here. Multiple R is 0.95. This is the absolute value of the Pearson correlation coefficient. The absolute value means it turns it into positive if it's negative. It states how well the two variables are correlated. This is a number between 0 and 1. And it is a square root of the R squared. Now what is the R squared? It's 0.902734. Okay, R squared here. Okay. And what is the interpretation of the R squared? This represents the percentage variation in Y explained by the X variable. For all X variables in if it's multiple regression, it's all X variables. In this case, 90.27% of the variation in Y is explained by X. So I just multiply this by 100, and I interpret it as percent variation explained, okay? There's also the adjusted R squared. You can read about it a little bit like this. Then we move on to the standard error. What is the standard error? Again, it's like the sample standard deviation of the regression model. Kind of like we had S before, but now we have, you can call it S if you want, but it's actually the square root of this MSE. And what is this exactly? This is given, is 13.82. This is, where is it? Standard error. Okay, it's right here, 13.82. And what exactly is the standard error? Well, let's go back here. I'm going to delete this. And let's draw the regression a little bit better so we kind of see it. Anyway, I have these points and I have this best fitting line. So the standard error, or this S, you call it, is roughly the average distance from the points to the line. Is the average of the residuals, in a sense, okay? How spread out are the points to the line? In this case, the 13 represents a value on the y, so they're about 13 units off on average from the line. That is your MSE. They're on average 13. Some are more and some are less. Okay. Okay. The standard error. Now, let's interpret. So this is a standard error, but actually these things can be computed from what you know as well, and I show this in the class, right? Okay, so now let's turn to the ANOVA table. What is the ANOVA? Oh, it's a little table here, right below this, which has some things that are redundant as well, that already computed in the top one. Let's first talk about this SSCOM. And what is this TSS, the total SS? So if I see here, I have this total. Do you see here? And the total, okay, it's 1573. This is the total sum of squares, it's called, okay? It's basically the sum, 15730. And if you go to the STATA, you also have it here, 15730. What is this? This is the total sum of squares. It is the total distance squared between each value y and its average value y, the average y value, okay? So basically, the TSS okay, the TSS is the sum of yi minus y bar, the average value of y squared. Now this might look familiar to you. It's actually a component of the sample variance, the numerator of the sample variance, basically. What does this mean exactly? Notice the best fitting line through the points, in this case, has a slope, but there's some average value of y here, call it y bar. And it's basically saying, okay, how well, okay, I know how well the points fit the line, okay, but how well do they fit the average? Okay, that is my total sum of squares. How well they fit the average. So it's each value minus this horizontal line, which represents the y bar. If that makes any sense, okay? Then, if we move on, there's this MS, mean squared total. Now what does this mean? This is basically, I divide this SS, divide by the degrees of freedom. So the SS total, the sum of squares total, divided by the degrees of freedom, which is 9, is equal to this. What exactly is this? Well, why is there 9 degrees of freedom? 9 because there's 10 observations and I subtract 1. And actually, now, what do I get? I get my S squared. This is the sample variance of the y. Is the sample variance, okay? That is your MS. And that makes sense because I only see how well the y bar is fitting the y here, so I just subtract 1 here, okay? Let's continue on. Okay, so this is the MST here. Okay, and you can compute it. You just divide by 9, right? And the answer was over there. Actually, it's not shown in the Excel file, but it's shown in the STATA file, which is interesting. Okay. Then moving on, there's the residual sum of squares as well. And the residual sum of squares, let's go back to the point, is related to the MSE, but is the total, not the average now. The total distances from the points to the line. So your RSS, called the residuals, or those errors, the error sum of squares, you can call them, some call them error sum of squares or residual sum of squares, okay? It means the same thing, but what are they? The sum of yi minus y hat. What is the y hat? Is the stuff on the line now. It's not the stuff on the average. So the y value here, for this point, this is the y hat I here. And this is your y bar for this point. For this point here, right? Okay. Anyway, this is the total distances squared from the points to the line. This is the sum of squared residuals. It's exactly that. It's RSS. The total. How many? The total distances of all the residuals squared. Okay? So how many are there? Lastly, we move to the mean square error, which was already computed from before. What is the mean square error? It's this one. But this is kind of the square root of the mean square error, okay? The square root of this one. So this is S. Now we compute this S squared, basically, but this MSE. The mean square is the average square distance of y to the best fitting line. So in this case, I just divide by n minus k. So I just divide by 8. And I get the mean square error. Okay? So in Excel, you see here the residual, and the mean square error is 191. Okay? So this MSE or MSR, you can call it the mean square, residual, is actually the standard error squared. So if I take the square root of this, I should get exactly this. And let's go back to the STATA output. And if we can see it, again, this 191, yes, this is the root mean square, they call it here, but this is just your S, the square root of this. So the square root of 191.25 should be exactly the 13.829. Okay, if you do this, you should get it. Okay. Okay. Let's see, we're almost done. Square the total means square the residual, and this brings us to almost our last topic, really. Regression sum of squares. What is this? It's the y hat minus the y bar. This is the total variation y explained by the x's. These are the square distances from the line to the average. Notice regression SS equals TSS minus RSS. So this reg SS you can compute from, if you know the total minus the residual. This is the reg SS. So in theory, let's go to the STATA. What is the reg SS? Is the model one. So notice the total is the model plus the residual is the total, basically, okay? Don't worry too much about this interpretation. It's not, at least my knowledge, is not that widely used. But if we read a little more here, we see as total variation y explained by by the x's, basically. Okay. And therefore, notice this implies that the r squared is kind of a standardized reg SS because I divide by the total SS. Okay. So this is the r squared. Also, the r squared is 1 minus RSS divided by TSS. And what is the logic here? This is also the r squared. You can compute it from these as well. So basically, this is saying if I divide this divided by this and I subtract 1 divided by this, I should get the r squared, okay? And what is the logic here? Recall that the TSS is equal to the total squared distance from y to its mean, y bar. It is the total variation in the dependent variable. This is just pure variation without taking into account any x variable, okay? Now suppose the variable x is able to explain some of this variation in y, okay? So this is the total variation. Maybe there is some positive average relationship between x and y. On average, as x increases, y also increases. Now if I add information regarding x, I create an upward sloping average line, which I just drew as the best fitting line. This way I provide more information for where y is. For example, when x is high, y is also high. Okay, it's more information. Therefore, each individual y point is closer to the value on the line, y hat, than to the average value, y bar. It will be closer to y hat. Therefore, the r squared, the variation in y explained by the x variables, is related to how close the points are to the line, relative to how close they are to the simple average. Okay? In other words, the r squared is 1 minus this divided by this. Okay? Notice if all the points are exactly on the line, the distance here is 0, then r squared is 1. Everything is fitting perfectly. And this implies the correlation coefficient in absolute value is also 1. Everything is perfectly correlated. Okay? If there is some relationship between x and y, there is a correlation and r squared will be positive. Now consider another extreme case where there is no relationship between x and y. They're not correlated at all. Then the best fit line will be a horizontal line. That will be the best fitting line. It will be horizontal. The coefficient on x will be 0 as well. So your beta hat estimate will be 0. And only the estimated y-intercept, the alpha hat, will be some number. And is going to equal to the average y value, y bar, actually. So if you just, if beta hat is exactly 0, your best guess for your y hat, for your y-intercept, for your alpha hat, is going to be your y bar. Okay, if that makes any sense. In this case, the best fit line will correspond to the simply the horizontal average line for all possible x's, and all its y coordinates will be y hat equals y bar. Okay, and so these things will be equal here. These distances will be exactly the same, so that this is 1, and then r squared is 0. Okay, so the x doesn't explain anything additionally besides the simple average. That's how well the simple average can explain y. Okay. Another thing that we haven't really covered in class is this f value, and you can see it in the regression. So this is the last topic here. We already talked about this one here. So this f value is 74.24. We have not discussed in class, and it's not going to be an exam. The program computes an f test, an f value, and under new hypothesis that all beta coefficients are equal to 0. The alternative is that at least one beta is not equal to 0. This is now as to the f test and the ANOVA that tests if all means are equal to 0. Significant f test appears, in this case, all means are the beta coefficients equal to 0. So this is just an F test. We haven't really talked about it, so you don't need to know it for the exam. But this is what they're computing here. Significance, F. In theory, the coefficient here, from what I know, should be exactly the same as this one. This p-value in simple linear regression. Feel free to double check this one, okay? Because there's only one beta coefficient here, but its p-value on significance on the F should be exactly the same as this, okay? Let's see if this appears here as well. Okay, F. Oh, they should just show you. In this case, they show you not significance level of the F. Oh, okay, they all show significance level here. 74.25. Okay, it's the same. You can double check this, okay? Okay, and this is it for interpretation of Excel and STATA output.